So we're going to prove that when you differentiate x to the power of n, you bring the power down, so you get n times x to the power of n minus 1. You reduce the power by 1. So we're proving this law. And we prove by induction. So there's the usual 3 steps. Now in this case, step 1 is a little bit longer. So we want to check that it's true for n equals 1, i.e. is d dx of x to the power of 1, which is just 1, is that 1 times x to the power of 0. And remember, x to the power of 0 is 1. So we're checking when I differentiate x, do I get 1 as an answer? Alright. The way we do this is we have to remember that f dash x is the limit as h tends to 0 of f of x plus h minus f of x all over h. And that's d dx. That's the derivative of x. So we're interested in differentiating x, or x to the power of 1. So we set f of x equal to x, and we're going to fill in this formula. So f of x plus h is x plus h. So f of x plus h minus f of x, so the top line here is x plus h minus x. The x is cancelled, and that's just h. Alright, so we're just filling in this formula up here. So then f of x plus h minus f of x all over h is simply h over h, which is 1. So finally, f dash of x is the limit as h tends to 0 of f of x plus h minus f of x over h, which is the limit as h tends to 0 of the number 1. So that's just 1. So that's true. So that was probably the longest step 1 we've ever had on an inductive proof. If you want, you can compress all these and just go straight to this one if you like. When you're doing longer proof, when you're doing longer differentiating from first principles, then you know it's handy to go through the steps. So we went through them there. So for step 1 in this case, we had to differentiate from first principles using the formula and show that our rule above up here does actually give the correct answer. Alright, so it is equal to 1. So that's step 1 done. So step 2 is going to be where we just say suppose it's true for n equals k. So step 2. So assume or suppose, so assume true for n equals k, where k is bigger than or equal to 1, i.e. when you differentiate x to the power of k, you get k times x to the power of k minus 1. Alright, so this is our star. And step 3 now says show true for k plus 1. So show true for n equals k plus 1, i.e. when you differentiate x to the power of k plus 1, we should get k plus 1 times x to the power of k. So the way we're going to do this is we're going to use the product rule. In order to use star, we need to have x to the power of k, not x to the power of k plus 1. So we're going to differentiate x to the power of k plus 1 by breaking it up into x to the power of k times x. So we're going to call this u, and we're going to call this v. So we're going to do a product rule here now. So u equals x to the power of k. Therefore, du dx is equal to k times x to the power of k minus 1. And we know that because of star. So we know that when you differentiate x to the k, you bring the k down and you subtract 1 from the k, because that's what we said up in star back up here. And over here, v equals x, so dv dx equals 1, and that was by step 1. If you remember, in step 1 we said when you differentiate x, you get 1 as an answer. So now using the product rule and putting those two together, So that's equal to u times dv dx plus v times du dx, which is x to the k times dv dx, which is 1, plus v, which is x, times du dx, which is k times x to the k minus 1. So the first term is x to the k. In the second term, we have two terms with x, which put a 1 there in for the power. So because we're multiplying the x's, we add the powers, and we get k times x to the power of k. And if you factor out an x to the power of k, here we get k plus 1 times x to the k, and we're finished. So just to remind ourselves, step 1 here is the longest step 1 you'll probably see in an inductive proof. So in order to check that it's true when n is 1, we need to use differentiation from first principles. So we go through the whole rigmarole there, and we show that we do end up with the right answer. Step 2 then is the usual, and for step 3, what we do is we break up this x to the k plus 1 as x to the k times x, and then we do the product rule. We know that when you differentiate x to the k, you get this, because that was star after all, and we know when you differentiate x, you get 1, because that was step 1. Put them all together, and you get the answer that we're looking for.